Okay. So I hope, have you all done an algorithms course? So you know the order of big O notation, theta notations, and so I hope all of you. Okay. So first of all, what is a polynomial time algorithm? So as you would be knowing, polynomial time algorithm is an algorithm which runs in time polynomial in the input size. So the number of steps of the algorithm will be polynomial in the input size. So I hope you all know this. And so we will be looking at polynomial time problems. And what are those? So problems which have problems which have algorithms which run in polynomial time. So I am not going to formally define problems or algorithms, etc. I hope you all know the intuitive concept of these things. Okay. And what do you mean by polynomial time? So something like order of n raised to k for some k. For a k which does not depend on n, that is k doesn't depend on the input size. So do you know examples of such problems? Examples of polynomial time problems? Sorting. Okay. So how much time does it take? Any? Huh? Okay, something like order of n square. And any other examples? Searching. And how much does this take? Order of n. Okay. Okay. Let me just list down some graph problems which also have polynomial time algorithms. Example, the problem of reachability. So what is reachability? So given a graph G and two vertices, its input is graph G, two vertices u comma v, output on leaf, there is a path from u to v. So this notation there stands for there exists a path from u to v. So I claim this is also in polynomial time. So do you know how much time it takes? Order of? N plus m. Okay. Now, how do you do this? Okay. So, understood what he claims? He says that take a breadth-first traversal. You all know that. Okay. So, so now, yeah, so most of these are easy polynomial time algorithms, easy in the sense these are easier. But there are even very highly non-trivial polynomial time algorithms, which, for example, I'll just write because so given a number, check whether it is prime. So it's something of order n raised to 12. So the initial algorithm which was given is something of this order. Yeah, and hence it's of this algorithm is practically not that useful because of it's of time this much. So that comes to our next question. Why do people prefer polynomial time algorithms? So why do we all consider polynomial time algorithms? So why polytime? Okay, so one reason is that most of the polynomial time algorithms which we know are always of this form, something like order n to n cube, n square, or even order n. And very rarely polynomial time algorithms are of this form, something like n to the 12. Usually it lies something like n cube, and and most of these algorithms, when it's n cube, you can even very huge inputs you can compute in time which is, basically very fast we can compute most of it. So for example, even the number of, you can search for a number in the maybe list on all the names of all the people in this world, but still you will be able to search it very fast. Something like some 3 billion people, even then you will be able to search it very fast. So, so that's because of the fact that it takes very little time to do that. So have you seen this comparison between something like an order n cube algorithm and a 2 raised to n time algorithm? So it's a so let's just take n equal to something like 10 cube, so 1000. And let's see how much time each of these algorithms take. So this takes around 10 raised to 9 steps, and this takes around 2 to 1000 steps, which is something like, which is greater than something like 10 to I just made it 16 raised to 250 and approximated it by 10 to 250. So even even the fastest supercomputer currently can do something like 10 to the 15 steps per second. So which means this can be done in within a second in that supercomputer, whereas this will take time something like 10 to 2 which takes around 10 to 35 seconds, which is basically 10 raised to 35 by 16 to 16. Let's make it in a minute. It's basically made it into years, and this comes out to be around it's just approximated by, so this by 100, this by 100, and something, this by another 1000, so or even 10,000. 8. It's even says it's something even greater. Something like even, so I just made it into years. So just to multiply, make it minute, hour, days, and year. It takes around 10 raised to 220 years to run this algorithm for an input of size just 1000. And so anyone knows the age of the Earth? Huh? Age of Earth is something like 5 into 10 raised to 9 years. So imagine the difference between. So that's why this non-polynomial time algorithms are infeasible for our practical purposes. So that's why we all stick to polynomial time algorithms, which otherwise there is no use of any practical use of studying non-polynomial time algorithms. So now we'll come to what are called as decision problems. So these are problems which have an yes/no answer. Okay. So the output of the algorithm gives either an yes or a no. Okay, so So something like sorting is not an SNOW, it's not a decision problem, whereas the others are. So for theoretical study, we will always stick to decision problems rather than these are called as non-decision problems rather than non-decision problems. But you can always convert this into a decision problem. So you can always do that, but we don't have to worry about. We don't look at how. Now, so we come to another so another way you can define polynomial time problems are, so you all have studied about Turing machines. You don't know what a Turing machine is? Okay. So another way to define a polynomial time problem is problems which have Turing machine encodings which run in polynomial time. So any algorithm you can view it as a Turing machine encoding. So this is another definition of polytime problems. Problems which have deterministic So I claim that these two definitions are the same. This definitions and this definition and this definition. That okay. You have to go back and convince yourself that these two definitions are the same. Oh, is this clear? Or? Now, so let's look at another problem which is basically called as something Hamiltonian cycle problem. So do you know what is Hamiltonian cycle in a graph? Yeah. Okay. So he says that a Hamiltonian cycle in a graph is a cycle which traverses all the vertices exactly once. It's a simple cycle which basically goes through all the vertices. So simple cycle which traverses all vertices. You understand what I mean by a simple cycle? So, or cycle such that each vertex appears exactly once in the cycle. Okay, so given a graph, can you check whether it has a Hamiltonian cycle in it? So that is a problem which we are going to look at. So what is the input to the problem? A graph G. What should you output? Yes, if it has no other ways. So can you give an algorithm? Can you try to solve this? Yeah? Huh? Permutor. Okay, so give list down all the permutations of vertices and then check whether that permutation is a cycle or not. Okay, so he says that, so our algorithm is going to consist of 2 steps. Step 1, list a permutation of vertices. And step 2, check whether the permutation is a cycle or not. So, how many steps does this algorithm have? N factorial. Yeah, something like n into n factorial. So, let's put it as n factorial. So, say something like order of n factorial, where n is number of vertices. Right? You can even say this n factorial is much greater than 2 to the n, and so I claim that I claim that 2 to the n is not equal to order of n to the k for any constant k. Again, this is clear to everyone. So again, you have to go. So let's put it as an exercise, which you can go home and convince yourself. So convince yourself that this claim is true, if you are not already convinced. So clearly then this is not a polynomial time algorithm which we have given, right? And as you can observe, it's not useful in practice. It's not useful, this algorithm. So now let's look at a problem which is basically very similar So let's say the problem gets a graph G and a cycle C. So as an input we get a graph G and a cycle C. You need to output yes if C is a Hamiltonian cycle in G. Otherwise output no. So can you do this in polynomial time? This. You can. So that's basically the checking this part, right? It's basically checking our second part. And you claim you can do it in polynomial time. Okay. So we called this C a certificate for this. C is a certificate for this problem basically. This cycle is a certificate for this graph G for the problem Hamiltonian. So, so if someone gives me the cycle, then I can tell whether the cycle is a Hamiltonian cycle or not very easily, basically in polynomial time. So that comes to our definition of what are called as NP problems, which we'll later see what NP stands for. So this kinds of problems that for all. Okay, so we'll parse through this definition. So what does this say? This says that so NP consists of all problems which is a polynomial time algorithm, first of all, A, and what does that polynomial time algorithm doesn't say whether doesn't output yes or no. But it has it does something else. That algorithm, what it does is it takes the input x and if a polynomial size certificate y, so a certificate is like the cycle there, is given to it, then looking at both the input and the certificate, it can answer yes or no in time polynomial. So again, let's look at this question here again. Okay. So what is the polynomial time algorithm here? Here the polynomial time algorithm checks whether the cycle C is a Hamiltonian cycle in the graph G, and the certificate here is the cycle C. So for every graph G there is a certificate C. For every graph G which has a Hamiltonian cycle there is a certificate C. And a polynomial time algorithm which given the certificate and the graph G can tell you whether can output yes or no. So yeah, so when I say this thing, it means if and only if x is an x, so you understood what I mean by an S instance? All those inputs which give an S output. So what I mean to say is that it should not always output S. This algorithm A should not always output S. It should output S only for those inputs X which have a certificate Y, which also if you are given a certificate Y will output S. And if it's a graph which G which does not have a Hamiltonian cycle, whichever certificate Y you give, it should always answer no. Understood? If G is a graph which does not have a Hamiltonian cycle, okay, then it should not be outputting S. This algorithm should not be outputting S for some certificate you give. So it should be output no. For any certificate you give, it should output no. It's not clear? Let's look at examples and then let's see whether you understand. Or otherwise, we'll try to go through this definition again. Okay. So for Hamiltonian cycle, you know a certificate. What is the certificate to be given? Let's look at something else. Okay, for example, check whether a number is composite. You know what are composite numbers? Which are numbers which are not primes. Now, is this problem in NP? That is a question we ask. We try to answer. In that case, what is the certificate which one can give? What is the certificate and the algorithm which we are looking at? What is the certificate Y and the polynomial time algorithm A which we are looking at? If we can come up with those two, then you can say that it is an NP. This problem is an NP. Okay. Given a factor y, you divide x and see whether it's not 1. The quotient is not 1, and the quotient is an integer but not 1. Okay. So he has come up with an algorithm. What does an algorithm do? It's the polynomial time algorithm here. I'll go here. So given input x and y, what it does is divides y, divides x by y, and I mean and and checks whether x by y is an integer and x by y are not equal to 1. Okay. And y, what is y here? You can view the certificate as some kind of a hint. If someone gives me a hint, can you answer the question? So that is the size of the hint should be something like polynomial in the input. And given both the hint and the input, can you answer the now? That is what NP basically does. Okay. So now let's look at another question. I want all of you here to understand this, what we are going through. If someone is not able to understand, please tell. We'll just go through, list on few examples and try to come up with certificates. Okay. There's a graph has a click of size k. What is the certificate going to be, and what is algorithm? Yeah, whatever you feel still. So given a graph to you, if someone gives me something else, can you check whether, if someone gives you something else, can you check whether graph G has a k size click? A click on k vertices. So you can basically give a click on k vertices, and then, so that is going to be your certificate. So certificate is basically let's look at one more example, and that is okay. So have you seen this? Have you seen this problem? So have you seen this problem? No one has seen? So you have seen. Okay. So this is basically a formula on some variables x1 to xn, and the formulas are of this form. So C1 and C2 and so phi is a formula like this, where each of the Ci is equal to some where so 3NF so phi is a formula on variables x1 to xn, and y is written like C1 and C2 and some Ck, and each of the Ci is something like L1 or L2 or L3. And what is this Li? Li is something of the form xj or negation xj. So for example, a formula like x1 or x2 or x3 and x1 or negation x4 or x2 and something like this. And when do you say this formula is satisfiable? We say such a formula is satisfiable if I can give one or zero assignments to each of the xi's such that this entire thing becomes true. So in such a formula, can you give an assignment such that this formula is true? Can give an, if you put x1 is 1, if you put x1 as 1, then this is true. So, but if you make it like this, let's make it like this. This formula doesn't have a truth assignment, because whichever, if you put x1 as 1, then this formula is, in whichever way you put it, it won't have a truth assignment. So 3NF sat formula is given a Boolean formula, given a formula like this. Now can you say whether there is an assignment which will evaluate to true or false? That is a problem. So what is the certificate which you can give here, and what is the algorithm? Okay, so she is saying give an assignment. So certificate is basically an assignment to each of the variables. Okay. So then we can easily check. So that is a certificate here. So all these problems which we have looked at are problems which are in NP, because it has a certificate of polynomial size, and there is an algorithm given the certificate and the input which can check whether it is an S instance or not. So another way to define NP is the set. So our problems. So another definition of NP are problems which have polynomial time non-deterministic Turing machines. You know what a non-deterministic Turing machine is? You have all seen. Okay. So how does this work? Are these two ideas consistent? So I claim these two definitions are same. Why? So let's look at this direction. So what does the non-deterministic Turing machine do? Now we want to show that. So I mean I hope you're comfortable with. You have seen Turing machines and non. Have you worked with Turing machines? Have you seen Turing machines? No. You have seen, and you know what a non-deterministic Turing machine is? No. Okay. So if you're not seen, just leave it. We won't look at that. Yeah, I mean we won't look at that, but those who have seen that, I claim that these two are same. And if you don't see why, we'll discuss it later. You can come to me and we can discuss it. So this takes us to, now we read some. Okay, so what we have seen till now is we have seen polynomial time problems, we have seen NP. So, okay, so I mean the name NP comes from the fact that it is a non-deterministic polynomial time machine. So the name NP comes from this fact, from this definition of NP. Okay, so we have seen NP problems, we have seen polynomial time problems. Now what we are going to look at is, we are going to look at polynomial time reductions. So what are these? So polynomial time reductions are algorithms which are not, these algorithms are not S-no output algorithms. See, these algorithms take input instance of one problem and output input instance of another problem. And this algorithm runs in polynomial time, polynomial on the input size. So algorithms which take So what is it? This algorithm takes as input instance of problem Q and output input instance of problem P, and the algorithm runs in time polynomial in the input. So yeah, runs in poly time. So let's look at such an algorithm which takes okay, I'm not done with this. I'm not done with this definition, such that it should have one more property. So moreover, that S instance of problems are mapped correctly. So an S instance of problem Q is mapped to an S instance of problem P and vice versa, and that means no instance of problem Q are mapped to no instance of problem P. So that's clear. Okay. So in pictorially you can represent it like this, something like, so this is the problem 1, this is our problem Q, and these are our S instance, this is our problem P, and these are our S instance. All whatever from inside should map here, and whatever outside should map here. S should be mapping to S and no should be mapping to no. What is the advantage of this? Such algorithms? The advantage is that if I find a polynomial time algorithm for P, then I clearly get a polynomial time algorithm for Q. Is that clear? Is that clear? Assume I have a polynomial time algorithm for P, then easily I have a polynomial time algorithm for Q. What will I do? I get an input in Q, I just run this algorithm A, which I know runs in polynomial time. I get the input for P, input instance for P, and then run the algorithm for P. So totally I take only polynomial time. So that is why we study polynomial time reductions, and that's why it's important. So you don't have to come up directly with algorithms for Q. You can, if someone has already shown that there is a polynomial time reductions to P, then you have to worry only about algorithms for P rather than algorithms for Q. So we will let's try to give a polynomial time reduction from 3CNF SAT to our click problem. So let's run this. So we are going to give polynomial time reductions. So algorithm A takes 3CNF SAT problem instances and outputs the click problem. such that this has a satisfying assignment only if it has a clique of size k. So what is this clique problem? Which so the clique problem, the input is a graph G and a number k, and output is whether a clique on size S if it has a clique on k vertices. So we are going to okay. So okay, what does our algorithm do? So the input to our algorithm is a 3CNF set formula. So let's say our 3CNF set formula is of the form and such that each Ci is equal to again each of the Li so each of the Li1, Li2 or Li3 are of the form Xj or negation Xj. So given such a formula, I am going to output a graph G which has a clique on k vertices if and only if it has a satisfying assignment. Okay. How does our graph? So what are the vertices of our graphs? So we create vertices Vi1, Vi2 and Vi3 for all I equal to 1, 2, k. So there are k such terms, C1, these are called clauses, k clauses, and each of the clauses has 3. These are called as literals, 3 literals. So for each clause I create 3 vertices, Vi1, Vi2 and Vi3, where I is a clause. So these are going to be our set of vertices of the graph. Graph G is going to look like that. What are our, when do we put edges? We put edge between VIT and VJR if I and J are different, that is they are from different clauses. If I and J are different and Vij is not equal to negation of VJR. So what I mean is something like this should not be x1 and this should not be negation x1. It's not allowed. If this is x1 and this is negation x1, then we won't put an edge. In all other cases, we put an edge. So our algorithm, what does our algorithm do? Our algorithm takes this input formula and just outputs this graph. The graph has to just output these vertices and output edges just by looking at these two conditions. And firstly, I claim this algorithm runs in polynomial time, polynomial and the size of the input, size of the formula. Is that clear? This algorithm has to go through the formula and output three vertices per clause and then put edge just looking at these two conditions. So I claim this thing will run in polynomial time. That's not clear? Okay. Okay, so take it as an exercise and try to convince yourself that this runs in polynomial time. But more importantly, this is a more important claim. I mean, both are important, but the more non-trivial claim is this: phi has a satisfying assignment if and only if G has a clique of size k. So let's look at this direction. Why? So what we are going to show is that phi has a satisfying assignment. That will imply that G has a clique of size k. Did you understand this construction? No? Let's So give a small formula. Let's try to construct the graph which we are looking at. Tell some formula. Write myself. Our formula which we have written there. What is it? How is our graph going to look like? We are going to, so this is close 1, this is close 2, this is close 3. And our graph is going to look like this. So this is V1, 1. So this is our vertex V1, 2, V1, 3. So these are our 3 vertices, which basically corresponds to close 1 here. And V21, V22, V23. So are going to corresponds to close 2, and it's going to corresponds to close 3. And how do you put edge? We put edge if, okay. So will we put an edge between V11 and V21? Can we put an edge between V11 and V21? What is V11? It's going to x1. And what is V21? It's x1 bar. Will we put an edge between V1? No. Because of the second condition, we won't put an edge. But we will put an edge between V1 and V22. This edge is allowable. Because it's not of this form, but it's of this form. I and J are different. They are from the different clauses. Okay. So similarly, this will come here. And what about this? There will be an edge like this. And there will be an edge like this. This edge is allowed. Okay. So what are the conditions? The conditions are that the vertices come from different clauses. So that is the first condition. That is the condition I not equal to j. And what are the second condition? Second condition says that one is not a complement of the other. Okay. So we put an edge between V11 and V22, even though both are x2. It satisfies both the conditions because it's not one is not a complement of the other, and they come from different clauses. So we'll put an edge like this, and similarly we can draw like this. So again this will be allowed. This may not. This was not allowed. Sorry. From close, this is not allowed because this is x3 and this is x3 bar. Yeah, this is x3 and this is x3 bar. So this is not allowed. Okay. So we can put edges like this. Now to our claim that this formula has a satisfying assignment if and only if G has a k clique. When does the formula has a satisfying assignment? The formula has a satisfying assignment if each of the clauses has a literal which is assigned 1. So either this should be assigned 1. From each of the clause there should be at least one guy which is assigned 1. Then we are through. Okay, this is assigned 1 and this is assigned 1, and from each of the clause if there is one literal which is assigned value 1, then the entire formula is 1. Okay. Now pick the vertices which, so we know that phi has a satisfying assignment. So that means there is an assignment to the literal such that from each clause there is a literal which is assigned 1. Now pick the vertices which corresponds to those clauses, those literals. So we have picked x2 as here. So then it means we pick this guy here. We have put x1 bar as, so it means we have picked this. We have put x3 there, means we have picked this. Now I claim that the graph on these vertices is a clique on those k vertices. First of all, there are exactly k vertices which we pick because there are k clauses, and from each of the clause we pick one vertex. So claim that each of these, they form a clique. Why do they form a clique? They form a clique first of all because they are, the first condition is satisfied because they are from different clauses. Each of the vertex are from different clauses, so the first condition is satisfied. The second condition is satisfied because, why? Why? Because we know that both the literals are 1, and it can't happen if they are complement. If those literals are one is a complement of another, both the literals can't be 1 at the same time. So, so we know that they are, hence the second condition is also satisfied. So what it means is that for any two pair of vertices which we have picked, there is an edge between them, because both these conditions are satisfied in, and hence it's a clique on k vertices which. So that is again you have to go back and try to work this out, try to think about this more. So what we have shown is that if phi has a satisfying assignment, then it has a k clique. Now what about the other direction? So assume G has a k clique, and now can we prove that phi has a satisfying assignment? So we are going to pick a k clique. We pick the k clique first of all. We know that it has a k clique because we are going this direction. We have picked a k clique. And first claim is that they are from different clauses. Those vertices, each of the pair of vertices come from different clauses. Why? Because in the same clause there are no edges between each them. So for any two pair of vertices in the k clique which we have picked, they should be from different. Now since there is an edge between any two pair, it means that the second condition is also satisfied. That means any two vertices which we have picked are such that their literals are not of the form that they are complements. They are in this form. So now the claim is that the literals which corresponds to the vertices which you have picked, assign ones to those values and you get a satisfying assignment. Again, why does that happen? Because from each clause we have picked one literal and that literal is being assigned the value 1, and it is going to be satisfied because its complement is not there in any of the other literals which we have picked. So that proves other direction. So it's clear. Okay. So now we'll wrap things in another 15 minutes. So what we have shown is that what we have given is a polynomial time algorithm which can convert from one problem 3CNF SAT to the clique problem. So if someone gives me an algorithm to find the clique on k vertices, then I know that there is a easy algorithm for 3CNF SAT2. So that's clear. If you have come up with a clique, an algorithm to find clique which runs in say polynomial time, then I know that I have a polynomial time algorithm which runs 3CNF SAT2. So that comes to our another another definition which is important. This comes to a definition of NP-hard problems. So these are problems P such that from all NP problems So NP-hard problems are problems such that there are polynomial time reductions from any NP machine, any NP problem to. So there are polytime algorithms. There are polytime reductions from all NP problems to the problem P. So again, let's make it clear. What it says is that so it's something like a hardest. So what is the intuition behind the name? These are something like the hardest NP problems. Why? Because there are polynomial time reductions from any NP problem you give. There are polynomial time reductions to that problem. Since they are the hardest NP problems. Why? Because if I come up with an NP algorithm for those NP hard problems, if I come up with a polynomial time algorithm for those NP hard problems, then it means that all NP problems have a polynomial time algorithm. Understood? So P is our problem here. What it is that it has reductions from all NP problems. So these are our NP. From every NP problem there is a polynomial time reduction to P. Oh shit. Did you arrange for this? So and so these are something like a hardest NP. So we'll just write what are. So there is one more definition coming. So NP complete problems. So these are problems 1 which are in NP and 2 which are NP hard. So these problems are basically the crux of the hardest problems in NP. So if someone comes up with a polynomial time algorithm for an NP complete problem, it means that all NP problems have a polynomial time algorithm because of this reduction, because we know that there are polynomial time reductions too. So I mean, Cook showed that, a guy called Cook showed that 3CNF set Cook showed that 3CNF set is NP complete. So what it means is that, so he showed that it's a non-trivial theorem. It says that from all NP problems there is a polynomial time reduction to 3CNF set. And we won't look at the proof clearly. And so I claim that we just now showed that click is NP complete. Why? Huh? Sorry, I can't. Okay. So first of all, click is an NP. Why? So we saw earlier that it has a certificate. So click is an NP, which we saw very early. And just now we saw that there is a reduction from 3CNF set to click. Just now saw that there is a poly time reduction from. Does it imply this claim that there is a reduction from all NP problems? Yes, why? Okay. Yeah, so because Cook showed that there are polynomial time algorithms from all NP problems to here. So this is by Cook, because he has already shown that there are polynomial time reductions to this problem. What we can do is take this reduction and then combine it with this reduction, and you get this. So because Cook showed this result, we just have to show it for one. We have to just show it for one NP complete problem if we can show this fact. What we have basically shown is that there are reductions from all NP problems to click problem. So what we have really proved now is that click is NP complete. Click is a problem which is NP complete. And if so, it comes to the end of our lecture, but let's just try just 5 more minutes. First of all, why do we consider this NP and NP completeness and all those things? So clearly there are a lot of problems which we don't, as of now we don't know whether there are polynomial time algorithms or not, whether it has polynomial time algorithms or not. So and it's not clear whether we don't know whether Hamiltonian cycle has an NP as a polynomial time algorithm or not. But the question is, can someone very intelligent person in the future come up with such an algorithm? So somehow we have to guarantee that, I mean, maybe he can't come or something. We have to motivate ourselves that maybe he may not be able to come. So that is the reason for this NP completeness. So the reason is that, so see that the problems click and 3 CNF sat etc. If a very intelligent person comes up with such a polynomial time algorithm, what it basically means is that he has shown that all NP problems are basically can be solved in polynomial time. And since even after 40 years, no one has till now come up with any polynomial time algorithm for any NP complete problem, or even anything close to a polynomial time till now no one has shown. Because of that fact, we can kind of hope that, I mean, maybe they may not be able to, no one will ever be able to come up with polynomial time algorithms for NP complete problems. And so there is a second, but till now we have never been able to show that it is not possible to. So there is this question whether P is equal to NP or not. And if someone answers this question, then you are you will become extremely rich and extremely famous, whatever you prefer. And okay. Yeah, so no one has been able to show that NP complete problems can't have polynomial time algorithms too. So that is, and this is the most important question in computer science as of now. Yeah. So there is a secondly, there is a philosophical question too. Why means, what is that? First of all, what is NP? What is an NP algorithm? So NP algorithm says that it has if someone gives me a hint or a certificate, then I can do it faster. Whereas polynomial time algorithm doesn't have that help of a hint or a certificate. Now, the question is, I mean, a hint, does it really help or not? So that is kind of a philosophical question. I mean, will you be able to come up with a hint in polynomial time itself? So, I mean, is it clear that if you come up with a hint, that hint in polynomial time, then you are done? So, question is whether a hint is helpful or not. So, okay. So that is a reason for. Okay. Yeah. So. Yeah, but interestingly, there are a lot of problems which are NP complete. So I mean, which are practically needed. There are a lot of problems which are practically needed, which are NP complete. Hence, we don't have. But what can we do? They are in NP complete, and we have seen that they will take at least 2 raised to n time to run, and if it is 2 raised to n, you can't do anything much. So now, but still, I mean, there are questions which we need to use it practically. So I mean, what to do now, and such questions are answered by some other. I mean, lot of other. So you can basically maybe think of approximating algorithms. You don't want the algorithms. You don't want exactly algorithm. You say if it's an integer output question, you want only a number which is very close to the correct output. And so there are a lot of such things, and I think randomized algorithm there it's being taught, right? So the course in random. So that is another way to get away with NP. So what we want is, we don't want exact. We want the correct answer only with high probability, and we want to say no wrongly only with very low probability. We want to say a wrong answer only with very low probability. And there is another thing called parameterized complexity, where you look at, I think it will be a course offered, right? Someone is giving a talk on parameterized complexity. I think so. Someone is giving a talk on parameterized complexity. So that is another way to work around the NP issues. I hope that you will see soon. Yeah, that's it. Yeah, so if you have any doubts, you can come to me. I will be in 110.